Oftentimes in physics, it's easier to deal with energy than it is with forces per se, because energy is a scalar, while forces, accelerations, torques, those are all vector quantities. Um, so when we can get away with something that's going to be easier to think through, we should probably do that. Things are complicated enough as it is. With energy, you can have is an unknown things like speed or position, um, because kinetic energy is dependent upon speed, and often potential energies are going to involve a position. So you can use conservation of energy based in the work energy theorem to solve a problem to answer those sorts of questions, without having to uh, go back to the more fundamental level of sum of forces is equal to mass times acceleration, or sum of torques is equal to rotational inertia times acceleration. So I want to make sure we have a clear thought in our mind for what the work energy theorem and energy looks like for case of rotations. So work uh, is a change in kinetic energy. And if it is purely rotational motion, then these are rotational kinetic energies. So you have a half I rotational inertia times angular speed omega squared. So that's one thing that we have to keep in mind. We can have kinetic energy in rotation. The work performed by a torque, we would arrive at that work by integrating the torque over the angular range of the displacement that the torque acts through. And if the torque is a constant, then we can just pull it out of the integral and you have a trivial integral of basically delta theta to tell you um, what the work is. So integral of torque over an angular interval gives us the work done by that torque. And then we can also talk about the instantaneous rate that work is being done, which is power. And the power associated with a torque, you just look back to this equation. If I'm going to take a time derivative of both sides, so the power is the rate that work is done, I can, uh, if the torque is constant, pull that torque out, and then we'll just have delta theta over delta t, which is going to give us angular velocity omega. So for linear motion translations, we had that the power, the handy relationship that the instantaneous power is the dot product of the force with the velocity. And for rotations, we have a similar cute little relationship that the instantaneous power is the torque times the angular velocity. All right, I'm going to go through a couple questions meant to illustrate um, how to think clearly about what forces and torques do. Um, so these are little thought experiments. Um, we're going to take a force F and apply it to a dumbbell for a fixed interval of time, but we apply the force in different locations. So in case A, the force is applied at the center of mass of the dumbbell. And in case B, it is applied at just one end of the dumbbell. Okay. The first question we want to wrestle with is, in which of those cases, A or B, does a dumbbell acquire the greater center of mass speed? So case A, or when the force is applied in case B, or does it not matter? Or are you not able to answer the question because we would need to know more about the rotational inertia of the dumbbell? So think about what you think the answer is, and then talk it over with your physics friends, and then we'll compare. All right, it makes no difference. And let's make sure that we understand why. If we go back to um, the impulse momentum theorem, So I've got a force applied over a time interval delta t. So that's the impulse, right? That impulse is the same in case A as in case B. And what does that impulse do? It changes the momentum of the center of mass of the system. So that impulse, which is identical in A and B, gives me a delta P. And that has to be identical in cases A and B. So it doesn't matter where the force is applied, the dumbbell is going to have the same center of mass speed after that impulse is acted. Okay, so then you might, legitimately wonder, well, what is it that the force is doing different in B than in A? And that we will try to illustrate with the next question. All right, so now forces applied to a dumbbell for a time interval, uh, the same for both. That is first as in A, and then as in case B. In which case does dumbbell acquire the greater energy? So case A, apply the force the center mass. Case B, apply the same force for the same time interval at one end of the dumbbell. And in which case does the dumbbell acquire the greater energy? So think it over, talk it over with your physics friend, and then let's compare. All right, there's greater energy in case B, and this is the important point I'm trying to get to with this pair of questions. Um, Forces don't get used up. Okay. If a force can change momentum, it changes momentum. If a force can cause a torque, it causes a torque. A force will do all the things that it can do. There's no conservation law for forces, they don't get used up. So in A, all that the force can do is change the center mass, the velocity of the center mass of the system, gives it some momentum. It does that. In case B, the force is placed asymmetrically. It can cause a torque. It does. It changes the center mass velocity, just as happens in A, and it also sets the dumbbell into rotation. So in case B, the dumbbell has both a translational kinetic energy, the same as in case A, and it has a rotational kinetic energy. So in case B, the dumbbell has greater energy. And that's an important point to try to remember. Forces don't get used up. If a force can cause a torque, it does. There you go.